Welcome back. This is CET 4333. This is our first lecture after exam 1. I have graded your exam 1. I'm very happy with your grades actually. However, I want you all to review your exams, and if you see any issues or you feel like I misunderstood you or I took points off that I shouldn't have, contact me. It's no problem. I'll review it and I'll tell you why I took the points off, and I explain it to you so it is clear so we all learn it. All right. What I want to discuss in this lecture is the chapter 3 topics. As I said it at the beginning of the semester, from chapter 3, I'm going to only cover machine characteristics and performance, and that's the main thing that I want to discuss. And also, I would like to talk about RISC versus CISC. RISC meaning reduced instruction set computer versus complex instruction set computer. And then most of the chapter is about an example of CISC multiprocessor, which is a Motorola MC68000, and an example of RISC computer, which is a SPARC or Sun computer, which we are not interested in discussing in a specific computer in this course. So I want to cover those parts, and that would be the chapter 3, which I'm hoping to wrap it up in this lecture so we can start emphasizing on chapter 4. All right. There are some practical aspects for the machine cost effectiveness, and we want to know what is it is extremely important that for every dollar spent in manufacturing, building, designing a computer system, how much work for that $1 we're going to get. Okay, how much? It's important that I know for any extra dollar that I spent, how much more work I get. And the way we calculate that one, it's really through performance analysis to see how much better a system performs for extra dollar that I spent. So we're going to look at the speed up. Speed up meaning if I made some improvements, meaning I spent some money, made some improvements, how much more percentage-wise in performance I'm going to get. That's one thing I want to look at it. And also I want to look in this part about the calculation of the total execution time. How do we calculate total execution time? Manually. Okay, that's another thing that I want to discuss. Now, regarding some issues that when we design a computer, those are compatibility, and there are two issues. One would be the hardware related. Most of the hardware expenses goes to mounting, case, keyboard, that kind of stuff. Integrated circuits, designing those are the hardware costs. Regarding the software, the main issue is upward compatibility. And that's the binary compatibility, source compatibility, emulation compatibility, meaning a software that I have created now for this specific hardware that I'm designing, that software should be compatible with the newer versions that I'm going to create. Or, in other words, or it should be able to run on a previous subsections. So we always have, there is a window that we want to make sure that whatever we build, it's good from, let's say, yesterday till tomorrow's design. So there is some time that we need to have that design to be compatible. Compatibility is an important factor. Now, the performance, anytime we talk about performance, it is really a strong function of application, meaning, for example, we design a computer, it is really designed for the softwares that are output oriented applications. Or we may design a processor that is really good for mathematical calculations. So always when we talk about performance, we need to be concerned also in what applications. Okay, the computers that, for example, let's say air traffic controllers are using, mostly input-output driven applications. All kinds of inputs coming in, coordinates of every plane in the air, and certain instructions going out to each one of them. So that system is totally different than a system that is calculating a lot of calculations, constantly calculating many, or it's based on the computation. All right. So those designs are different. For that reason, we say always we say performance is a strong functional application. Depends on the application. And when we design a computer, usually that's how we design them. Except the computers or PCs that we see in every office, these are general purpose computers, and they're good for everything, but they're not the best for any single application, but they're good all over. Some of the performance measurements or the measures that we use, one is called MIPS, or millions of instructions per second. So same job may take more instructions on one machine than on another, right? It depends on how you design. Remember, we're going to see this, we're going to make more sense out of this when we cover chapter 4. That means if I want to perform an add instructions, right, how many instructions is going to take me to perform that simple one-line instructions in the C language? Another measure is MFLOPS, or million floating point operations per second. And then there are some benchmark, certain known programs, application-oriented programs, that when we design these systems, we run those programs and we calculate the execution time to see where the program, where our design has a shortcoming, or where it's performing better than what we expected, and to gather that information. One is known as Whetstone, which is a program made up to test the specific performance features. The other one is Rystone, or synthetic competitor for Whetstone, made up to correct Whetstone's emphasis on floating point. And then you have a spec, which is a selection of real programs, many programs that in different fields of science, and we run those programs to see how the design is performing. Our design is, what's the performance? Quantitative performance measurements, as I said, if I design a computer that executes a program, let's say 20% faster than the other one, we say that 20% is the speed up, right? How do we calculate the speed up? Here is the example that the book used. Consider two auto routes. The old one, which allowed an average speed of 34 miles per hour, and the new one, which permitted 46 miles per hour. What is the speed up of the new one over the old one? Always we say the speed up is the speed on new route divided by speed on old route. So S sub new, S sub old, 46 over 34, it comes to 1.35. This means there is a 35% speed up. But what we could do to get to that 35% directly, instead of reading it this way, we could say, okay, speed up, percent speed up is equal to S of new minus S of old divided by S of old. So that would be times 100. So 46 minus 34 divided by 34 times 100. That comes directly to 35%. And that shows the speed up. Now, here is if you remember, we said the frequency or the clock tick is reciprocal of the clock period, or vice versa. All right. So here's what we are saying. Many measurements are in terms of time, t. it takes to accomplish some task. Recall that time t is the reciprocal of the speed. So S is 1 over t. If the improvement is measured by recording travel time rather than travel speed, the equation changes as follows. S of new over S of old, then if it is reciprocal, then 1 over t of new, 1 over t of old. And or exactly the same way, t of old minus t of new divided by t of new. And you remember that it looks different because you see that S of new is 1 over t of new. And then when you do that one, the old comes on the top numerator and t of new goes to denominator. Unlike the previous one, the old one was in denominator and new one was on numerator. Here is some example. A certain computer system takes 125 milliseconds to render a certain graphic image. And this time is reduced to 100 milliseconds when a graphic processor card is added to the system. What is the speed up? T of old over T of new, 125 over 100, 1.25, or a 25% speed up. Or we can do T of old minus T of new divided by T of new times 100, and that will give you directly 25%. This is the speed up. How about the execution time? Execution time is always equal to the number of instructions, the number of the clock cycles per instructions, time the period of a clock period, the time the clock period, tau. Okay? And here goes the example. For example, we say the master clock in a certain computer system is increased in frequency from 700 megahertz to 1.2 gigahertz. What is the speed up due to this improvement if no other factors such as memory access time interfere with the improvements? Well, old IC, that's the T of old, right? T of old over T of new. T of old, it's IC times CPI times tau of old. IC times CPI times tau new. Since IC and CPI hasn't changed, only clock frequency has changed. So that would be, so this is the period, right? So that would be 1 over 700 because we said that tau is equal to clock period is equal to reciprocal of the clock tick or frequency. So 1 over 700 over 1 over 1200, and this gives me 70.1% speed up. All right, here are some CISC and RISC I said we'll talk. What's the complex instruction set computer? Many complex instructions and addressing modes. Some instructions take many steps to execute. Not always easy to find best instruction for a task. Sometimes, for example, add instructions in a CISC model, we may have 15 different instruction types. So you need to find out what's the best one, all right? So you have to design your software based on that. You design the controller in your CPU to perform based on that. We're going to see those in chapter 4, so you will understand better what I'm saying. While in RISC computer, few simple instructions and addressing modes, usually from one word per instruction, may take several instructions to accomplish what CISC can do in one, because these are simple, right? Complex address calculations may take several instructions, usually has load store general register instruction set architecture, meaning only 2 instructions have capability of accessing directly memory, and that's load and store instructions. And we have general registers on CPU. Here this design calculus risks. Simple instructions can be done in few clocks. A pipeline design can allow instructions to complete in every clock period. Pipeline means at every clock cycle you fetch one instructions, but you hold them someplace till the currently executing instructions is executed and completed. This way we don't have to wait till we go fetch another one. But there are problems, hazards with that one. You may have a fetch an instructions, and then by the time you decode that instructions, you find out it's a to-go instructions. You have fetched a number of instructions that you have to trash them actually. And usually have fixed length instructions, simplify fetch and decode. The rules may allow starting next instructions without necessary results of the previous, and unconditional executing the instructions after a branch, and starting next instruction before register load is complete, which refers to pipelining. And it goes through some other risk characteristics that I want you to read in, and then never mind about this part anymore. We don't care about this part because this goes to the whole thing is discussing the case for the Motorola 68000 and Sun computer, which we are not interested about any specific computer design in this class. Now, there is a problem in your chapter 3, problem number 3.1. I am going to solve that problem here. Then I'm going to post some homework related to what we discussed here, and so you can exercise those homework problems and get ready for exam 2, because in exam 2 I'm going to ask some of these questions. Let's see if I can get the document camera up. Okay, here's the chapter 3, a problem from chapter 3. It says, a program contains the following instruction mix: 20% load store instructions with the execution time of 3 nanoseconds each, 70% ALU instructions with execution time of 2.1 nanoseconds each, and 10% branch instructions with execution time of 2.3 nanoseconds each. If the clock period is 500 picoseconds, calculate the average CPI for the program. And also in part B asks you, what is the average MIPS rate of the program? Remember we said these are the measurement, some of the parameters that is used in measurement. So I'm trying to show you what it means. So the problem says a program contains the following instruction: 20% are ALU instruction, and each takes 3 nanoseconds to execute. Then we have 70% of the instructions within that program are ALU. Oops, this is 20% are load store instructions. 70% are ALU instructions, and each take about 2.1 nanoseconds. And then 10% are branch instructions. Each will take 2.3 nanoseconds. Okay? The question is, if the clock period is 500 picoseconds, calculate the CPI. How do we calculate CPI? It's very straightforward. CPI is equal to average execution time of one instruction divided by clock period. Okay? CPI, that's the clock cycles per instructions, right? That's what we are calculating. What's the CPI? Remember that we said T is equal CPI times instruction counts IC times CPI times tau. So how do we calculate CPI? So it's equal to average execution time. How do we calculate average execution time of one instructions? It's very straightforward. We said 20% or load store instructions. On the average, they take 3 nanoseconds. So times 3 plus 70% or ALU instructions. On average, they take 2.1 nanoseconds plus 10% or branch instructions, so 0.1 times 2.3 nanoseconds, okay, divided by 0.5, because we said it is 500 picoseconds. I just converted 500 picoseconds is equal to 0.5 nanoseconds. Okay, you divide that by 1000, you get this. So CPI is equal to 4.6 clock periods per instruction. Now, this was part A. Part B says calculate the average MIPS rate. Average MIPS rate is equal to 1 over CPI times clock period times 10 to the power of 6. All right? This is the formula we use. So it's equal to 1 over 4.6 times clock period. It is times clock period times 10 to the power of 6. However, I want to calculate this one in terms of the nanoseconds. So it would be 500 times in terms of the seconds, because average MIPS rate per second. So I'm getting this one, if this picosecond times 10 to the power of minus 12 picoseconds, right? This is the clock period times 10 to the power of 6. And this comes to 435 MIPS. Right. In here, I just made sure that if the time here is nanosecond, this is in nanoseconds, because time doesn't matter. This is clock period per instruction, right? There's no, so all I have to make sure that the numerator and denominator are same units, because what I was getting is the CPI. However, in calculating the average MIPS rate, you're calculating per seconds, million instructions per second. So clock period, I had to convert into seconds. 500 picoseconds is equal to times 10 to the power of minus 12 seconds. Remember, look at my first notes that I posted in the in that one. I discussed these units. You do calculations and you are done with this part. That's all I want to discuss about chapter 3, and I will post some homework. It should be available to you by tomorrow and or maybe later on today. So please work on the homework, and then try to learn this one as soon as you can. So I want to move on to chapter 4. My next lecture will be on chapter 4. See you in next lecture.